Welcome to episode 33 of Introduction to Quantum Field Theory. This will be a really short one because I didn't realize how short the section or how not in depth the section was, even though it's like it's a few pages long. I was reading through it, and a lot of the information is just stuff we are is like stuff that you don't necessarily need to know. Like there's a lot of fluff to it, but yeah. So we'll just be talking about really how you create a gauge interaction, really simple, and then we'll expand what it looks like for a scalar field. Really, there are two things you do. The first is you assume a free field Lagrangian, and this can be a free field for spinors or scalars, and then you perform this map where you take the derivative, the gradient, and you bring it to this. This is the covariant derivative. So you map to this. This is the covariant der- derivative. Yeah. And then you simply add the free gauge field Lagrangian. And those are the steps. So let's see how this works. Suppose we have the free scalar field, which is 1/2 partial mu phi minus m squared phi squared. I don't like that. Phi, that's better. That's a better one. I don't like this one either. There we go. So we take this, and then we just plug in 1/2, and we get partial mu minus I e a mu phi partial mu. This will be here minus I e a mu phi minus m squared phi squared. And this, if we expand this fully, then we get, and I'm going to go directly to the final result because this is just a FOIL thing. It's a simple FOIL where I put this in here and then I multiply 4 elements together. So um, foiling is not too difficult. We just get partial mu phi and then partial mu phi minus 2i eps or e partial mu phi a mu phi and then minus e squared a mu phi squared minus m squared phi squared. So this is what you get when you introduce a gauge interaction. And recall what gauge fields kind of do, with this gauge or covariant derivative. This basically says that I can change the coordinates of the field wherever I am, and change the coordinates and still have the same physics. But when you let the coordinates be their own field, you end up with it being the vector potential. The electromagnetic potential ends up being that field that encodes what these coordinates are. So the end result for a Lagrangian is going to just be this. Um, so this will be that, and we get all of this plus the electromagnetic um, yeah, plus the, or I guess it's minus the, there's a minus sign in the Lagrangian for this. So we get partial mu a nu partial mu a nu minus partial mu a nu partial mu a mu, and then close it off. And this is the gauge interaction.